Variables, as we have seen, store information that the programmer can then later call up and manipulate if required. Variables are simply reserved memory locations that store the values the programmer assigns depending on the data type used. There are many different data types available for the programmer in C++, such as an integer, floating point, boolean, character, and so on. It's widely accepted that there are 7 basic data types, often called primitive built-in types. However, you can create your own data types should the need ever arise within your code. The 7 basic data types are integer, floating point, character, boolean, double floating point, white character, and no value. These basic types can also be extended using the following modifiers: long, short, signed and unsigned. Basically, this means the modifiers can expand the minimum and maximum range values for each data type. For example, the int data type has this default value range, which is a fair value, you would agree. But now, if you were to use one of the modifiers, the range alters. Naturally, you can get away with using the basic type without the modifier, as there's plenty of range provided with each data type. However, it's considered good C++ programming practice to use the modifiers when possible. Well, there are issues when using the modifiers though. Double represents a double floating point value, which you can use for incredibly accurate numbers, but those numbers are only accurate up to the 15th decimal place. There's also the problem when displaying such numbers in C++ using the cout function, in that cout by default only outputs the first 5 decimal places. You can combat that by adding a cout precision function and adding a value inside the brackets. But even then, you are still limited by the accuracy of the double data type. For example, try this code. Build and run the code, and as you can see, the output is only 3.14159, representing cout's limitations in an example. You can alter the code including the aforementioned cout precision function for greater accuracy. Take precision all the way up to 22 decimal places with the following code. Again, build and run the code. As you can see from the command line window, the number represented by the variable pi is different to the number you have told C++ to use in the variable. The output reads the value of pi, as with the numbers going away from the 15th decimal place. This is mainly due to the conversion from binary in the compiler, and that the IEEE 754 double precision standard occupies 64 bits of data, of which 52 bits are dedicated to the significant, and roughly 3.5 bits are taken holding the values 0 to 9. If you divide 53 by 3.5, then you arrive at this value, recurring, which is 15 digits of precision. Well, to be honest, if you are creating code that needs to be accurate to more than 15 decimal places, then you would not be using C++. You would use some scientific specific language with C++ as the connective tissue between the two languages. You can also create your own data types using an alias-like system called typedef. For example, this code, when executed, creates a new int data type called meters. Then in the main code block, there's a new variable called distance, which is an integer. So you are basically telling the compiler that there's another name for int. We assigned the value 15 to distance and displayed the output. Distance in meters is 15. Well, it might sound a little confusing to begin with, but the more you use C++ and create your own code, the easier it becomes.